Hi all and welcome to our lesson today on defining secular functions with sine, cosine and tangent. Now actually the content in this lesson on the whole has like the first 5 minutes which is really useful, then the next 5 minutes or 10 minutes which will be like, yeah, okay, theory based, but might be helpful to know where things come from, and the last few minutes like, oh wow, that's how you use it, awesome, why didn't I know this from year 11? Okay, so this is a year 12 lesson dealing with circular functions, and it's about these defining. Now I don't know about you, but you guys really, if you're watching this today in years 10, 11 or 12, are so lucky. When I was at school, this here was the dream calculator. You were like, wow, that was awesome. It had scientific numbers on it. Before that, you were walking around with what we called a four-function calculator, which was literally a four-function calculator. Now you could use this scientific thing, this FX7, to be able to actually help you work out these sine and cosine things. You were no longer using what undoubtedly your parents were doing, and my parents were using log tables and tables of trig values and all sorts of horrible things like that. You know, can you imagine walking in with like a textbook size just to try and find out the sine and cosine of a value? Calculators change things, you know, but even though I had a calculator, there were some teachers, thank you Mr. Kurd, loved your lessons where you made us learn these are horrible table of values, right? So if you look here, and I'll come back more on that in a moment, but we had to learn all the sine, cosine and tan values in root notation or surd notation by heart. You have to ask, was there an easier way of doing it? Well, absolutely, I should cocoa, there was a better way of doing it, and they were two triangles. Now, why did nobody at my school turn around and go, okay guys, actually you don't need to learn that, there's an easier way of doing it? Oh, a British secondary education. Thank you so much. There we go, ladies and gentlemen. You can effectively use a triangle. Now, we know that if we draw a triangle with 30 degrees there, that must be 60, and there is my right angle. Why does it have to be a right angle triangle? Because I'm using trigonometry. The only angle I ever needed to remember was sine 30 degrees equals a half. And funnily enough, that was the one I always knew. Now, we know that sine is opposite over hypotenuse, and as such, if there is my 30 degrees, I know my opposite now is 1. So let's rub this little arrow out here. So I know that's now 1, and I know the hypotenuse is 2. And using a little bit of trigonometry, using a little bit of Pythagoras' theorem, I then can skip ahead and know that this side here is root 3. I can now use that information to find out the cosine of 30 degrees, because I know cosine is adjacent over hypotenuse. So the adjacent is root 3 and the hypotenuse is 2. And the tan of 30. And tan is opposite over adjacent, and the opposite is 1, and the adjacent is root 3. And lo and behold, there, knowing one tiny piece of information on how to draw a right angle triangle, have given me the 3 values for sine, cosine, and tan of 30. And the same thing happens with 60, right? If I use 60 degrees as my reference angle, sine of 30 is a half. There's 1, 2, and root 3. So I now know the sine of 60 degrees is, sine is opposite over hypotenuse. So opposite is root 3 on 2. Wow! The cosine of 60 degrees is given by the adjacent over the hypotenuse, which is 1 over 2, and that would give the tan of 60 degrees, which is the opposite over the adjacent, is opposite of adjacent root 3 on 1, which is just root 3. So much easier than, you know, doing what I had to do, learn tables. All right, I used to work with somebody, Tal, how are ya? Who basically showed me this method, and I was like, okie dokie. And what he was suggesting was, this is the way you could also remember. If you number the numbers 1, 2, 3 from 0 to 4, and backwards 4, 3, 2, 1, and 0. If you were to remember that this was 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees, which are the common degrees we actually want to use, and you do this all over a 2, and you remember the top line is sine and the bottom line is cosine, then what he is saying, and it has merit, it's just taken a long time just to actually draw this thing, but anyway, he is suggesting that we can find the cosine of 60 degrees by saying, well, here's the cosine column, so the bottom column, 60 degrees is 1, so you do square root of 1 over 2, which just happens to be a half. And is the cosine of 60 degrees a half? Well, I should go, yes it is. Okay, and what about the sine of 45 degrees? Well, the sine of 45 degrees, well, there is 45 degrees, so it's root 2 on 2, right? Yep, it sort of works. If you like that way, knock yourself out. But we can also use the triangle to help us find the exact values of 45 degrees. How? Well, once again, I only need to remember that the tan of 45 degrees is actually 1, which is the same as 1 over 1. And why is it important? Because it is opposite over adjacent. So I know that is 1 and that is 1. And it actually doesn't matter which 45 I use. Opposite over adjacent is always going to be 1. And then that would suggest that this would have to be root 2. And so I would know that the sine of 45 degrees would equal to the opposite over the hypotenuse, which would be 1 over root 2. Now, those of you who are doing specialist maths will then undoubtedly need to go on and rationalize the denominator, but in maths methods, we no longer have to do that. All right, what's this got to do with the price of fish? Well, the unit circle can actually help us find out all sorts of angles outside of the ones that we've just said there, 0, 30, 45, 60, and 90, all right? And the unit circle is great, but I know that lots of people in year 11 can meet this and go, Wibble, what? What are you doing? And why do you not say in the brain? So my advice to you is have it tattooed on yourself. No, I'm joking. Please don't. Undoubtedly, please tell me that this guy here did not really have the unit circle tattooed on his back. That would make me slightly nervous. All right? And why would you put it on your back? You would never be able to see it. Anyway, whole new discussion. So here is the unit circle, the basics. I told you, the first 5 minutes of this video, fab. That stuff was all important. This bit now is all about the basics. So, strap in. This is where the theory gets exciting. First things first, the unit circle is called the unit circle because it has a radius of 1. So here we go. Here is the circle. I know that anywhere on that circle, a line joining the center to the edge will always have the radius of 1. I call this angle here, any angle that is drawn, I look for the angle between the line and the x-angle, all right? And the x-axis, sorry. I call that the reference angle. Why? Have no idea. I'm sure I must have heard it somewhere, but I like that now to be called as the reference angle. And what we find out is, if we were to draw a triangle, a right angle triangle, where that is 1, if we call this x and we call that y, then what we then can say is, well, look, x, to find x, we have the adjacent and the hypotenuse. If that is theta, if this is theta, this is my adjacent and that's my hypotenuse. And adjacent hypotenuse is cos. So we know then that cosine of theta would be equal to the adjacent x divided by my hypotenuse is 1. And we like the fact that hypotenuse is 1 because then I end up that x is equal to cos theta. In exactly the same way, we work out that y is equal to sine theta. Right? Just by using sine is opposite over hypotenuse, and the opposite is y divided by the hypotenuse is 1. And we use the formula that tan theta is equal to sine theta divided by cos theta. So in this situation, we would say that tan theta would be equal to y divided by x, right? All really important stuff. But how does this help us with finding exact values for the unit circle? Well, again, so we now know that any distance along the x-axis can now be said to be the cosine of the angle, right? So you would argue the smaller the angle, the bigger the value of x, right? That's the Think about it. Smaller the angle, there's my value of x. That's quite big. If I actually have this line here and bring it down, I notice my x value is smaller. Bigger angle, what do I notice? My x value gets smaller and smaller and smaller, right? So the smaller the angle, the bigger the value of x. Wow! And we now know that my y value is actually the vertical distance. And again, what are you saying? So if I have my unit circle here and this line here, and I draw a dot here, then I know that that distance there and that distance there have something to do with sine and cosine. Right. Okay. So, what does that have to do with the price of fish? Right. Well, here we go. Imagine I have 0 degrees there. Now, the unit circle is always actually measured anti-clockwise. Right? You go around it anti-clockwise. So 0, 90, 180, 270 slash 360 degrees. So if I want to find the sine of 0, if I want to find the sine of 0 degrees, I'm going to firstly draw a line at 0 degrees. And I'm going to say to myself, now, I know that cosine is horizontal and sine is vertical distance. Well, this line here is flat. There is no vertical distance. So in which case, the height of that is 0. So the sine of 0 is 0. Wow! What about the sine of 90 degrees? Well, the sine of 90 degrees. The first thing I'm going to do is I'm going to draw a line at 90 degrees. And I'm going to say to myself, right, using the center as the distance between, as the reference between horizontal and vertical height, if I'm doing a vertical line, how far across am I moving? Well, 0. Not interested. How high am I moving? 1. And you're going to say, well, where'd you get the 1 from? Remember, this is the unit circle. So the distance all the way along is 1. So I now know if sine is a vertical distance and it's going 1 high, then a sine of 90 must be 1. What about the sine of 180 degrees? Again, there we go. It's a line. It's a horizontal line. It's flat. It has no vertical distance. So the sine of 180 must be 0. And what about the sine of 270 degrees? Well, there is my 270 degrees. It has a vertical distance of -1. Why? Well, again, remember, this is 1, 1, -1, and -1. We're counting 0, 0 as the center of my circle. So it's almost like overlaying the unit circle on the Cartesian plane. So sine of 180 degrees is 0, sine of 270 degrees is -1. That is freaking awesome. But what about the cosine of these angles? Well, there we go. Bow wow. 0, 90, 270, 180, and 270 degrees. Thank you very much. So what do we want to find out? Let's find out the cosine of 0. There we are. There's the cosine of 0. Now, cosine is a horizontal distance. Does that line have a horizontal distance? I should Coco. It's 1 long. Does it have a vertical distance? No, but I don't care about the vertical distance when I'm doing cosine. It's just the horizontal distance. What about the cosine of 90 degrees? Well, there is my 90 degrees. Has it gone any vertical distance to go from the origin to that point? No. So the cosine of 90 is actually 0. And you continue working around the unit circle in that way to help you. I think it's just brilliant. But what about, finding angles between, say, 90 and 0 or 0 and 90 degrees? Well, okay. So first things first, there is 0, there is 90, there is 180, there is 270, and there is 360. Now notice that 0 and 360 actually share each other. That's quite important. Right. So what I'm now going to do is I'm going to actually say that my x values are now going to be called A, and my y value is going to be called B. So rather than x and y, I'm just going to call them A and B. And as we've done before, we know that x is equal to the cosine. My y is equal to the sine. So I'm going to say my cosine values are now A, my sine values are B, my tan values are B over A. Why? Well, just remember that B over A is because that tan theta is equal sine theta divided by cosine theta. Right. So great, that's useful. We're going to use that as a reference. But what about now moving on to angles between 90 and 180 degrees? All right, so we've said that we're going to let this here be, so x was going to be A, and that was going to be B. So these I'm now going to use as my reference for the rest of my triangle. So first things first, I'm going to draw a line on here where that theta has been reflected in my y-axis. So I now know that that angle there must also be theta. If that's also theta, it's really useful because I'm using the x-axis as my reference angle all of the time. So ideally, we now need to say, well, how would I describe the point on that circle that I'm looking at, right? The unit circle is really, really important. How would I reference it? Well, if I know that this here is pi, and you can say pi, what do you mean pi? Where did pi come from? Well, remember that we can actually do things in both degrees and radians. So normally we talk about the unit circle in terms of radians. So that's 0 radians. 90 degrees is pi on 2 radians. 180 degrees is pi. That's 3 pi on 2. And that's 2 pi. Now, if you're not sure why, just remember that 360 degrees is equal to 2 pi radians. So 180 degrees is equal to pi, and in which case 90 degrees is equal to pi on 2, and then you can use that information to go around every 90 degrees by doing pi on 2, pi, 3 pi on 2, and 2 pi. Okay, so this angle here, this point here isn't quite at pi. In fact, it is pi minus theta. I can actually reference that angle now as being pi minus theta. Why theta? Because this is my initial reference angle. We like this. It's a base angle. It's a reference angle. And we know that this is exactly the same side. Right. Okay. So knowing that, because we got this as a unit circle, I can now draw a triangle. I can draw a triangle. And I'm just going to delete some of this here to make it a little bit more clear. If I know that this angle, call it 1, is the same as angle 2, then I must know that this height here now is equal to b. And I would know that this length here must be minus a. Why? Well, because on this triangle it was a, and because we're using the Cartesian plane, it would be minus a. Ah, right. So hold on a moment. We can then say, well, we now know that sine of pi minus theta. Remember, sine is my vertical distance. And my vertical distance is equal to b, right? We've just read that off of here. We would know that the cosine of pi on theta will be equal to, cosine is horizontal distance. Horizontal distance is minus a. And I know that tan of pi on pi minus theta would be simply equal to sine over cos, which would be b on minus a. Well, what has that actually got to do with the price of fish? Well, hold on a moment. We already know that b is exactly the same as sine theta. So that's the same as sine theta. We know that a is cos theta. So that must be minus cos theta. And beyond that would actually be, well, equal to minus tan theta. So that's where these three identities come from. We can say that the sine of pi on theta, sorry, the sine of pi minus theta is actually exactly the same as theta. The sine of theta. So if I know the sine of theta, I can find out the sine of pi minus theta. Wow! And the cosine is minus cosine, and tan is minus tan. Well, this is phenomenal. This is really, really helpful. Well, we can continue. We can now look at this quadrant here, between 180 and 270 degrees. What I'm going to do is I'm actually going to draw a line that extends straight on. Why? Because I now know that that's theta degrees. I'm going to draw a right angle triangle. We now know that this here is minus a, but if this here is b, and it's going below the line, then that must be minus b. Actually, let's write that in a slightly different place so we can actually see it, Darren. So minus b. How do we reference this angle? What do we call this angle? Well, it's pi plus theta. Why? Because, well, I've gone from pi and I'm adding on theta. Why am I using theta? Because this reference angle is actually going to be the key to everything we do for this unit circle. So I can now use this information to say, well, we know that cosine of pi plus theta, well, cosine is equal to a horizontal distance that's equal to minus a, because we've got my horizontal distance here. We'd know that sine of pi plus theta would be my vertical distance, which would be minus b. And then I would know that tan of pi plus theta would be sine minus b on minus a, which is b on a. But again, we can go back to what we actually said a moment ago. We know that minus b would be equal to minus the sine of theta. We know that minus a would be equal to minus the cosine of theta. And actually, that would be simply the tan of theta. OMG. So what I'm actually finding out is that minus sine theta, minus cos theta, and tan theta. Now what I've noticed is here, that should be minus sine theta, and that should be plus, right? Silly mistakes. All right, I think I've copied that down incorrectly from another circle. But we now have three identities here, and another three identities here that actually is starting to help me find out all the different angles between 0 and 360 degrees, or 0 and 2 pi for this triangle, for this circle. And the last one, same thing. I'm going to draw a line there. I now know that this is theta. It makes my life easy because I now know that the x value is a, whereas that's b, that's now going to be minus b, and we use the same idea. How am I going to describe this? Well, it's not quite at 2 pi, so it's going to be 2 pi minus theta. So the sine of 2 pi minus theta, well, the sine of the unit circle is the vertical distance, so that is negative b. I've got this cosine of 2 minus theta, so the cosine of 2 pi minus theta is equal to a, because it's the horizontal distance, and that would give me that the tan of 2 pi minus theta would give me sine divided by cos minus b on a. Let's reference it back to our original values here. So minus b would be minus sine theta, a would give me cos theta, and minus b on a would give me minus tan theta. So again, what we're saying is, if I need to find the angle that's 2 pi minus theta, I actually can just work out minus the tan of theta. So this is another three important pieces of information. That actually is the basis of the unit circle. But we sometimes like to actually re-express these bottom three in a slightly different way. Now, why? Because we said the sine of 2 pi minus theta, for example, was minus sine theta. But we know that 2 pi is the same as 0. So then, if we do 0 minus theta, we get minus theta is equal to minus the sine of theta. So again, if I wanted to work out the sine of minus 30 degrees, then what this would suggest is that that's the same as minus the sine of 30 degrees. Mind blown. Okay, so these are all really, really important, but what does it have to do with the price of fish? Well, all stations to Canberra, basically, or cast, or cats, or acts, or anything. What we tend to find is using the unit circle between 0 and 90 degrees, sine, cosine, and tan angles are all positive. Between pi on 2 and pi, or between 90 and 180 degrees, we find that actually the only angles that are positive are sine. So all of my sine angles are positive. In this quadrant, between pi and 3 pi on 2, we find out that tan are all positive. And in this one here, we would find out that cosine are all positive. And hold on, if I change this to all stations to Canberra, that actually helps us work out for all of my angles whether they're going to be positive or negative in each of those quadrants. So I now know that in this quadrant here, any angle that if I find out between cos of, let's say, what is that, 280 degrees, I know my answer is going to be a positive value. Right? I don't know what the value is. I'd have to use my calculator or other methods. But I'm just trying to say, but if I wanted to work out the sine of 280 degrees, I would know that my value would work out being negative because it's in that quadrant. Right, important things to note. Sine is an odd function. Cosine is even. Tan is odd. We'll come back to those some of the time. So, evaluate the sine of 3 pi. Well, 3 pi, remember, this actually only goes between 0 and 2 pi. So to go to 3 pi, I'm actually going to go round the circle and then back, and I'm going to end back at pi. So the sine of 3 pi is exactly the same as the sine of pi. Oh my goodness. Now the sine of pi is the vertical distance of that line there. So in fact, the sine of pi is 0. Easy peasy lemon squeezy. The tan of minus pi. Well, when you're doing minus pi, you're actually coming this way around your circle. So minus angles actually just go clockwise. Counterintuitive, but isn't that true of all of maths? So I am looking for the tan of minus pi. Well, in which case, I can use that information because I know that I can find the sine of pi and the cosine of pi. How do I know that? Well, because remember, the sine of pi is my vertical distance, which is 0, and I know my cosine of pi is my horizontal distance, which is 1. And because tan is 0 is sine over cos, that's 0 over 1, which gives me the wonderful value of 1. And you're going to be screaming at saying, no, you made a mistake. And actually I have, because it's -1. We've come backwards on ourselves. So that would be -1 as well. So the tan of pi minus pi is in fact -1. You see how we're using the unit circle? The exact value of sine of 3 pi on 4. Right, 3 pi on 4. So there is 0, there is pi on 2, there is pi. Well, 3 pi on 4 is 3/4 of pi. So that would suggest that if I draw a line here, which is going to be in that segment, that this one here, that there is going to be pi on 4. Why is this important to me? I've stated it over and over again. We are always interested in our reference angle. So we're always interested in actually having an angle and finding out what these angles here are. Always really, really important. So I now know that if I can find this angle here, which is pi on 4, I can find this angle here. How come? Right. All stations to Canberra. So automatically I know that the sine of pi minus pi on 4, which is the same as 3 pi on 4, must be exactly equal to the sine of pi on 4. Why? Because in this quadrant, all of my sine values are the positive, and I know that so long as I've got this reference angle here, that they are the same. Whoa! Well, the sine of pi on 4 is 45 degrees. Draw a quick triangle. There is 45 degrees. I know that's 1, 1, and root 2. So the sine of 45 degrees is the opposite over the hypotenuse, which is basically 1 over root 2. Whoa! Write down the exact value of cos of 5 pi on 3. 5 pi on 3, so 0. What have I got here? I've got pi on 2, I've got pi, I've got 3 pi on 2, and I've got 2 pi. So 5 pi on 3. Whoa. Well, that's going to be the same as the cosine of pi plus 2 pi on 3. The cosine of pi plus 2 pi on 3. Oh, okay, so 2 pi on 3. That doesn't help. Trick. Right? Reference angle here. So the question is, would you agree that 2 pi minus pi on 3 would be the same as 5 pi on 3? Well, of course it would, because it would be 6 pi on 3 minus pi on 3. And we know that a minus pi on 3 gives me this one here. So that's pi on 3. We can draw my reference angle here, which is now pi on 3. So I now know that the cosine of 2 pi minus pi on 3 is going to be exactly the same as the cosine of pi on 3. All I need to do is check whether it's going to be positive or negative, right? Because this is the one we want. So it's all stations to Canberra. Canberra's positive in that one. So that's going to be positive. And pi on 3, well, pi on 3 is 60 degrees. So there's my 60 degrees. There's my 30 degrees. What is it? 1, 2, and root 3. So I want the cos of 60 degrees, which is caught a herring, which also happens to work out as a half. Right now, you can go on and do these yourself without using a calculator. Evaluate the sine, the cosine, and tan of 150 degrees. Nothing more difficult. There's my unit circle. It's now in degrees, so it's 0, 90, 180, 270 / 360. You want 150 degrees. So work out where 150 degrees is. I think it's there. That means that that angle is 30 degrees. I'm looking for my reference angle is 30 degrees. I'm trying to find sine. So I know that I'm going to find the sine of 30 degrees because that's my reference. I know that's equal to a half. But where is this 150 degrees sitting? All stations to Canberra. So in which case, because sine is positive in that quadrant and I'm trying to look for the sine of 30, it's equal to a half. The cosine of 30 degrees, right? Exactly the same thing. Sorry, the cosine of 150 degrees would be the same as the cosine of 30 degrees, but negative because it's only sine is positive in that quadrant. And the tan of 30 degrees Likewise, I'd have to work out minus the tan of 30 degrees because of that. Wow, 30 minutes. Thanks very much. I look forward to seeing you next time. Thanks so much for joining us for that video. It was really good having you. Now, if you'd like to know when the next video is coming, why not click on subscribe? Alternatively, head on over to MaffsGuru.com where you can watch all of the videos on its own dedicated website. While otherwise, watch the video that's just popped up. It'll be part of this series. All right, take care. See you again soon.